Hi, welcome to our third session on continuity and differentiability. We've had two sessions earlier where we talked about some of the techniques of differentiation, and if you had not watched them live earlier, you have the link shared on Edmodo, and I expect that you would find time to go through it and do the required practice as a follow-up, so that when I see you in July, you would be ready to answer and attempt any of the questions based on those techniques. Today we are going to talk about, to begin with, a certain special style of questions which would bring back maybe logarithmic differentiation, and some of them may even require implicit differentiation only. And then we will also talk about the second derivatives. That is, if I know what the first order derivative is, how do we find the second order derivative and what exactly it means. Also the questions that are based on it that are usually tested in exam. That is going to be our agenda for today. So to begin with, I would like to just remind you once again that you have a Q&A app that runs on the right side. You can post your questions alongside, and I will try to take a look in between and answer. At the same time, if I ask a question, then please take a moment to answer it, work along, and be with me so that the topic becomes much more clear to all of you. So if you are ready to go, then I would start by sharing the presentation, which also would be uploaded on Edmodo later, and you can always refer to it if and when you need. So here we are. All right. So we are going to talk about something called as differentiation of infinite series. So we are going to cover a few questions which just look a little different. How and where the word infinite would come up, we will be able to see that as well. And they will be very easy to recognize as you go along. So let's just start with our first question. We have here y is equal to x raised to the power x raised to the power x going right up to infinite number of times. And you have to find y by dx. So how do we find the derivative of such a function? And that is where, if you look at what I started by saying, we are going to be looking at differentiation of infinite series. So here the function is expressed as an infinite series. So there is a pattern that you observe in this expression. And we have to find the derivative of y with respect to x. Now, infinite series and infinite expressions are always very interesting to use and to identify. In this case, it's the infinite series that is actually going to make the task so much easier for us. So if you're able to recognize what is going to be our starting point here, then I would request you to post your response on the side. So look at the Q&A bar that's running on the side, and let me know what exactly makes you work from this step. How would I start finding the derivative of y with respect to x? How do I make this function more comfortable for you to work with, something that you are familiar and can get started with? So what should I do to begin the work? Any clues? So also it would be nice to know who all are present today. So if you can just look at the on your right side and just enter your name so that I know who all are present. I can see 3 of you have joined me right now. So if I can see who all are present along with me, then it'll be nice to know and I can interact with you personally. Otherwise, well, of course, I'll always assume that you are listening and following everything that I have to say. So if I may just have your names on the side, let me see if you are able to read and hear. Can you see the slides and can you hear me alongside? And can you also suggest what should my starting point be for this particular problem? Where do I go from here? Anyone? If you can just get me a go ahead, then I can just carry on. Otherwise, well, I may just do something and you may not be able to hear or see, and then it would be quite a waste of time for everyone. So, right, so we have Lakshita here. All right, could you see and hear? I guess yes. Okay. So if we are good to go, then maybe we can relook at the problem and give me an idea as to where do we go from here. If y is equal to x raised to the power x raised to the power x, and it goes on infinite number of times, how do I start off so that I am in a position to find the derivative of such a function? That is the challenge for us right now. So if you think about infinite series in this case, then you're looking at that only working for us. If I hide away one of the x, if I don't write one of the x there in the expression, then where does it go? Right. Welcome, Tanmay. This is only for you that I'm doing this activity in the afternoon. So hopefully you have done your job of the morning and is back with me here. So we are looking at our first question where we are looking at finding the derivatives using things that we have learned earlier, techniques as logarithmic differentiation, also looking at implicit differentiation playing alongside. So yes, taking log always helps, but at the same time, can we rewrite this function knowing that x raised to power x goes on infinite number of times? And therefore, the entire function which is in the power, can that be looked at carefully and said as to what it would become? So what would this function y be rewritten as? So if I think about x raised to power x going up to as many times as I want, then obviously it will not really matter if I skip the first x that's in the base and replace the rest of them that are coming in the power as our y. So if I rewrite this function before I take log, I can rewrite this as y is equal to x to the power y. And if you take log first, perhaps you would still be able to do the same as what I'm going to come up with. So what we are looking at is, why do I need log first of all? We need logarithmic differentiation when there is a function of x raised to the power a function of x. So this is a very classic example of that. And therefore, before I find the derivative, I'm going to take log of both the sides. And once you do that, then things get just going. So I have log of y is equal to log of x raised to power y. And therefore, we can rewrite that as y times log x on the right hand side. And we are good to go for derivative. So why don't you take a moment and figure it out on a piece of paper, and I will show you the solution as well in a minute. So take a look at how do we proceed from here and what would the derivative be equal to. So differentiate both the sides with respect to x. And as you differentiate both sides with respect to x, you are looking at log of y derivative using chain rule. On the right hand side, y times log x, so product rule. These are two rules that are going to stay with us all through. And therefore, once you finish off the differentiation, you would get something like 1 over y dy by dx on the left, and on the right hand side you will again have dy by dx times log x plus y into the derivative of log x, which is 1 over x. And the task is to find dy by dx. So since we are dealing with implicit differentiation, obviously the requirement would be to collect dy by dx on one side and have it separated out, and your final answer would be something like y squared divided by x times of 1 minus y log x. Right? So let's see if you also got the same answer. Did we? So, any doubts here before I proceed to my next question? Are we all good with it? Okay. All right. So, I think I will then move on to our next problem, and that also is an infinite series. So take a look at this one and see if you are in a position to simplify and then find the derivative. So y is equal to square root of cos x plus square root of cos x plus, so everything is coming inside the first square root and then the second square root, and this series goes on infinitely many times. You have to prove that dy by dx is sin x by 1 minus 2 times of y. So again, where do we rewrite, how do we use the idea of this infinite series and rewrite our function before we start with the process of differentiation? So any ideas, guys? How do I simplify this function? How do I rewrite this function so that I can start off with the derivative? Give me a clue on the side. Give me an idea where and what should I write y as. Do I see the function repeating in this pattern? And if I do that, then can I rewrite this y in a simpler form? Anyone? All right, great. So if you have also got the same answer for the previous question, and if you can focus on the present one now, what would you get? How do I rewrite y again? Y is under root of cos x plus under root of cos x plus under root of cos x going on. And so if I think about rewriting using the y again in the function, then this y can be rewritten as exactly root of cos of x plus y. So if I keep the first cos x as it is and replace the rest of the series with y, nothing has changed. And once that's done, then we are ready to go for differentiation. Choice is yours completely. You may differentiate it as the function is right now, but you also have the freedom of squaring both the sides and rewriting the function as y squared is equal to cos x plus y. And now when you find the derivative of both the sides with respect to x, you would get 2y dy by dx is equal to negative sin x plus dy by dx. And then it's just a matter of simplifying, and you get your final answer as derivative of y with respect to x to be sin x by 1 minus 2 times of y. Right? So that's a very simple one. You may even find a problem like this asked as a 1 marker. It's very rare that a function like this gets very complex and time consuming as far as the derivatives are concerned. So here there are 3 functions that I have put down, 3 problems for you to note down, because these questions are not there in your NCERT textbook. So you may note them down and give it a try later. Maybe if you have a problem or want to compare your answers, then you may put maybe just take a picture and post it on Edmodo, because typing the solutions may be a problem. but the answer must come out to be exactly what it is given here. So you will be able to verify your working alongside and be comfortable with dealing with it. Right. So I can see that you all are very much with me. You are able to answer and get the exact solution. Right. Tanmay has said it should be square root of cos of x plus y. Exactly. If you put the brackets carefully somewhere, there is exactly everybody who's able to get it. Fantastic. So please note down these three questions and give it a try, and I think you will be quite happy to go ahead with it. So give me a go ahead before I change my slides. If you have all noted down the question. Okay. I think now I will move ahead. In case you have missed out a particular problem, you would definitely be able to get back to it from Edmodo. The presentation would be up, and the recording of the Hangout session also will be available just in case you want to check it out once again. So let me proceed with our next topic for the day, and that is to understand what does it mean to find the second order derivative and what kind of problems are we going to deal with. So here we have a function, a very simple algebraic polynomial function in this case, and I have fx is equal to x cubed plus 3x squared minus 5x plus 7. We know what f dash x is going to be. So in this case, as you can see, f dash x turns out to be 3 times x squared plus 6x minus 5. Now this again is a function of x. So if I have found out the derivative of y or f of x, will it be too complicated to differentiate it? Given again, and as you can see, the f dash x turns out to be a function of x. So if I can again find the derivative with respect to x, what would happen? What will I get? So in this case, f dash x is 3x squared plus 6x minus 5. And if I again differentiate, that is find the derivative of f dash x with respect to x, from a quadratic, I have reduced it down to a linear polynomial now. That's definitely changed. At the same time, what you have done is you have found out the rate of change of the instantaneous rate of change. So f was a function of x and you found f dash x, which was the finding the instantaneous rate of change of f with respect to x. Finding the derivative again would still mean the same. You have found out that instantaneous rate of change of f dash x with respect to x. So in terms of physical quantities, it would simply be in terms of the rate of change, we are looking at the second derivative to represent nothing but acceleration of a moving body. So it's basically telling you the rate of change of the velocity. And that is something that we will be referring back to once we start dealing with application of derivatives. So if I know that there is a function f of x, I can find f dash x and I can find another derivative of it. And in fact, this process can go on. From second derivative, I can find third order derivative, which in this case would be 6. Fourth order derivative will actually be 0, right? So the process kind of stops for this. But that's only when you're talking about polynomial functions. If I talk about trigonometric functions, sin x differentiates to cos x would differentiate to negative of sin x, and then the process just kind of oscillates between sine and cosine functions with a plus and a minus coming in between. At the same time, symbolically, we use the notation of f double prime of f x, that is f double dash of x as it is read, or f double prime of x, and also it is written as and read as d2y by dx square. So we rewrite and read this function as, that is the second derivative, as d2y by dx square, right? And alternately, the notation that we will use will be f double prime of x. I'm used to reading it out as f double dash of x, so you may find me reading it more or in that form. So both of the notations are used alternately as and when needed. At the same time, if I had started by calling my function instead of f of x as y, then f dash x would be represented as y1, 1 as a subscript. And y2, where 2 is written in the subscript, would represent the second order derivative. So that is how the notations would follow. And what we need to do is just start off with a basic set of questions. So here we have a problem where you have to find the second order derivative of tan inverse x, and another problem along with it where you have exponential x into cos of 3x. So why don't we start with tan inverse x? To find the second order derivative, it's essential to first, of course, find the first order derivative. So in this case, dy by dx is nothing but 1 by 1 plus x squared. So I need to find second order derivative, means I have to find the derivative of 1 over 1 plus x square all over again. And how does one do that? How do you find 1 by 1 plus x square derivative? You are all perfectly capable of doing that, right? The only thing that you need to use is either the chain rule or use the quotient and then chain. So in this case, the second derivative is the derivative of 1 over 1 plus x square. Using the quotient rule, it turns out to be negative 2x by 1 plus x square whole squared. So in this case, there is not much that one need to worry about or to work with. But these are very basic functions that you would constantly be using. So if I may now move on to the next question, which is exponential x cos 3x. It's a product of two functions. So to find dy by dx, I use the product rule. And before I find the second order derivative, one may just rewrite this function as exponential x into cos of 3x minus 3 sine 3x. So then I'm not doing the product rule twice, but I have taken exponential x out and I have now rewritten this as product of two functions. Choice definitely remains yours, but what you are going to do now is find the derivative of the function, in this case of both the sides again. So we're looking at d2y by dx square. Using the product rule again, you end up with an expression which does simplify. So exponential x derivative is exponential x as it is, cos 3x minus 3 sine 3x remains as it is, plus exponential x as it is, and then the derivative of the second function, which will be minus 3 times sine 3x minus 3 times cos 3x. I think this should have been, there is a mistake here, right? There should have been a, when I differentiate sine 3x, there should have been a 3 times cos 3x, and I have already had a 3 here. So this will become minus 9 times cos 3x. So I'll request you to just ignore this final expression and take a minute and simplify this all together again and see what your final answer turns out to be. So just excuse me for that typing error, but please note that sine 3x derivative itself is 3 times of cos 3x. So you must have a 9 coming in there, right? Great. Okay, let me now take a look at some of your questions. Do we have a doubt anywhere with anyone? You were not able to read question 3. Okay. And all right, let me see what we can do about that. So let me get back to the questions on the side here. So Tanmay says that he is not able to read question 3. Is that so? So question number 3 of the presentation, is that so? All right, so what we'll do is we'll show you that slide all over again, or you can again take it down from the presentation on Edmodo, if that is all that is the problem. Is that so, Tanmay? All right. And everybody else has noted down the problems. So maybe maybe when we wind up the session, we will again look at that slide, or I'll take you back right now. And that's perfectly fine. You can deal with that, not a problem. Any other doubt in terms of the concepts that we have covered so far? No. All right. So let's then get back to the presentation and see what else can be done with the second derivatives. All right, we have another interesting problem here. And I call it interesting because it would recall few of the things that you had done earlier. It's a good question to test how good are you with chain rule of differentiation, because there is nothing else but chain rule of differentiation that is needed here. So y is given to be log of x plus a root of x square plus 1 whole square. And you have to prove that this expression holds good. Now, in this expression, you will find first and second order derivatives both appearing. And there are two different ways of dealing with this question. I'll try to elaborate on that as we go along. But to begin with, none of the methods would work unless you first find what is dy by dx, right? So why don't you go ahead and give it a try and see what dy by dx is going to be, given y is square of log of x plus root of x square plus 1. Take a minute and find the derivative of this function. All right, have you given it a try? Because this needs to be looked at very, very carefully. When you find dy by dx by the chain rule, it will be twice of log of x plus root of x square plus 1 into the derivative of the inner function, which is log of x plus root of x square plus 1. And then we again follow with the chain rule. So what's the derivative of log of a function of x? Nothing but 1 by function of x into the derivative of that function with respect to x. So if you keep track of the chain that's been following, now I have to find the derivative of x plus under root of x square plus 1. And what's the derivative of x plus root of x square plus 1? I will have that again by just taking the derivative of the sum of the two functions. So that's 1 plus 1 by 2 root of x square plus 1, and then the derivative of x square plus 1 again, which turns out to be nothing but 2x. So you get this long expression, 2 times log of x plus root of x square plus 1 into 1 by x plus root of x square plus 1, and into, keep the brackets very, very carefully, 1 plus 1 by 2 root x square plus 1 into 2x. So if you just take a look at it, obviously this 2 and this 2 would get cancelled. And a little bit of LCM simplification done here would lead to lot of simplification, and it would become something like 2 times log of x plus root of x square plus 1 into 1 by x plus root of x square plus 1, and here also in the numerator you will get x square plus 1 plus x. So this expression in the numerator and here in the denominator would get cancelled, and your dy by dx will be 2 times of log of x plus root of x square plus 1 into 1 by root of x square plus 1. Now, what you are looking at is this as your target statement. You want to prove that 1 plus x square into d2y by dx square into plus x dy by dx minus 2 is equal to 0. So this is what we want to achieve. Now, there are two ways of going ahead, and you have to learn to be a wise chooser so that you know that there are alternatives which can make your work much simpler. If you pay attention to this expression, you will realize that nowhere this log of x plus root x square plus 1 kind of an expression appearing. So somewhere there is a relief that is going to come through the derivative that we have found out. So one way of going ahead would be to keep the function as it is and find the second order derivative, which would mean product rule, which will mean again the derivative of log of x plus root of x square plus 1 to be found out, etc. And then you substitute what you have for the second and the first derivative and check that everything balances out and works out to be 0. What I'm going to show you is a better alternative. What I'm going to tell you is to use what y was. Y is square of log of x plus root of x square plus 1. I already have log of x plus root of x square plus 1. So what if I square both the sides of this function? I would get square of dy by dx is equal to 4 times of square of log of x plus root of x square plus 1, and this simplifies to be 1 by x square plus 1. And now you can also replace this entire function where you have a log of x plus root of x square plus 1 whole squared with y, and therefore your entire expression simplifies to a very nice and compact expression. And not only that, before you go ahead with your second derivative, you may cross multiply so that you avoid the quotient rule. Product rule is always easier to follow than quotient. So this is the trick to do these questions in a more efficient manner. Square, use what your y was, and then cross multiply before you differentiate. But at the same time, keep an eye on the question. What is the final answer that you need? That would be a guiding point for many of the problems. Now, if I differentiate both sides with respect to x, then using the product rule, on the left side, I have 2x into dy by dx whole square plus x square plus 1 into the derivative of the square of dy by dx. Now, that is the function that you need to be careful with. How do I find the derivative of square of dy by dx? So again, by the chain rule, it will be 2 times dy by dx into the derivative of dy by dx. So that again is what is required to be understood, and therefore you will have 2 times dy by dx into d2y by dx square here. Right hand side also gets differentiated to 4 times dy by dx. And then we are almost done. You just have to simplify, so you can divide both sides by 2 times dy by dx and rewrite, simplify so that it looks like the expression that you've been asked to prove and establish. I will request you to maybe give the same question a try by the other approach, that is without squaring and without rewriting the function, and see the difference in the ways you end up simplifying the expressions. You would find that this method that I have just illustrated turns out to be a much efficient method over the other one, because there the working can get quite detailed and you can end up going number of sheets in terms of the work and may not end up with the right answer as well. But it is worth a while to give it a try and then accept what I have shown you right now. All right, so any questions, anyone here? If we can take a look at your Q&A here. I think all of you are good with whatever has happened so far. I haven't seen anyone coming up with any doubts here. So if you have, you can always post alongside and I will stop in between and take a look if I've not been able to explain anything completely. So what we are going to look at in the next few minutes are some more questions where the same idea is used, but now I'm talking about derivatives. In fact, the second order derivative of functions which are parametric functions. So you can see how this section that we are doing today is going to be really the end of this chapter, because it's kind of revisiting logarithmic, chain rule, quotient rule, product rule, and now the parametric differentiation as well. So how do I find the second order derivative? And now in this case, add a particular value of theta, which is pi by 4, where the functions are parametric functions. So if x is a cos cube theta, y is a sin cube theta, you have to find the second order derivative of y at x as theta is equal to pi by 4. So to begin with, we do recall that dy by dx for parametric functions is nothing but dy by d theta divided by dx by d theta. So obviously you will first find the derivative of both x and y with respect to theta. So in this case, that turns out to be minus 3a cos square theta sine theta and 3a sine square theta cos theta. So dy by dx is a quotient, which simplifies to be negative of tan theta. Now we are fine so far as the first derivative is concerned. Now this is a stage where you have to be very, very careful of what we are going to do next. You have to find derivative of dy by dx with respect to x. But dy by dx is a function of theta. X is also a function of theta. So I have to differentiate negative tan theta with respect to x, but x is a function of theta. So I'm looking at two functions, dy by dx and x, both being functions of theta. So there is again a parametric differentiation that's going to come in. So in the second order derivative of parametric functions, again the derivative, that is a first order derivative, if it is again a function of theta, the parametric differentiation needs to be brought in. And in order to simplify and understand it in a different way, let me call dy by dx as z. So to find second order derivative of y would be same as saying finding the first order derivative of z now. So I have to find dz by dx. Z is a function of theta and x is also a function of theta. And if I just take a look at, no, I think there's a difference or some error in the slide. Dy by dx was minus tan theta, right? So let's stick to this rather than the earlier, some incorrect typing here. So this should have been minus tan theta rather than minus cot theta. Let me change it right now so that you are not confusing them. Right. And now I have to find the second order derivative. So dz by dx is nothing but dz by d theta divided by dx by theta. So dz by d theta is going to be nothing but same as the derivative of minus tan theta, that is sec square theta, divided by minus 3a cos square theta sine theta. which will be same as simplified 2. If you replace by theta the value as pi by 4, it will all get simplified and will take a value as 4 root 2 by 3a. If we just check the calculation again, this should have been a minus tan theta. And if I just correct it so that there is no confusion in your work as well, and I have to set the sign correct. And when I differentiate dz by d theta, I should also have a negative in the numerator, right? So your final answer therefore will be positive. Are we good to go with that? And so your final answer would be positive 4 root 2. And that's what your final answer would be. So sorry for that incorrect typing in between somewhere, but that is what your final answer is. So you're looking at a corrected set of slides, and you have d2y by dx square at theta equal to pi by 4. So at theta equal to pi by 4 would mean that you replace theta by pi by 4 and then find out whatever the final value of the second order derivative is. Right? Take a moment and see if you have got on to what we have done right now, and if that works out for all of you. So this is a minute correction that needs to be done, and we are good to go. So take a second look at what we have done. dy by dx was a function of theta. So in order to find the second order derivative, if I take this dy by dx to be, say, a function called z, then I have to find the derivative of z with respect to x, but x is a function of theta. So the parametric differentiation again comes in. dz by dx turns out to be dz by d theta divided by dx by d theta. Simplify, and when they say find the derivative's value at theta equal to pi by 4, just plug in theta equal to pi by 4 and simplify your final answer. That's all that's needed to be done for such cases. All right. Okay, let me see if you have also noticed things that were going wrong in between, and if you have also corrected and got the right value. So is there anyone want to ask? All right. So before I show you the next question, Tanmay, I'm taking your doubt here. So you said there's one doubt I want to save for the end. So don't save it for the end. Ask it right now. What doubt do you have? If you can ask me, I'll just answer it for you. Just type it out on the right hand side in the Q&A bar. Are you there, Tanmay? So Tanmay has a doubt and he wants to save it for the end, but I do have one more question to do today before we wind up for the day. But at the same time, it will really help, Tanmay, if you can just type it on the side and we can get going with it. I'm not able to see any doubt that you have put on the side. So if you can just retype your problem or doubt, or somebody can just +1 that post where Tanmay had posted his doubt, then I can take it. Otherwise, I'll just go ahead and finish off with my question. And in the meanwhile, you can just type in your doubt and we'll be good to go from there. So I will come back to the Q&A, but right now, let me just finish off with one more question. Because we had done inverse trigonometric functions earlier, so there must be a question on inverse trigonometric functions for second order derivatives as well, right? So here we go. The problem is if y is equal to square of sine inverse x, prove that 1 minus x square into d2y by dx square minus x dy by dx minus 2 is equal to 0. So these are very standard style of questions. You are given a y and then you have to prove an expression which involves the first and the second order derivative. So to begin with, we find the first order derivative, dy by dx. Chain rule gives you 2 times sine inverse x into derivative of sine inverse x, which is 1 by under root 1 minus x square. Now, how do we proceed from here? What should I do to find the derivative? As I want to find the second derivative, in this case, we'll be able to see that there are 2 options. I can find the derivative as a quotient rule, or if I have picked up something from the previous examples, there is a possibility to simplify this expression and use the fact that y sine inverse x whole square before I jump to the second order derivative. So if I cross multiply and if I square both the sides, you would be able to see that your function becomes much more simplified. You get 1 minus x square into dy by dx whole square equal to 4 times sine inverse x whole square. And that is what really makes a difference. You get this y back in, and now your expression is so much more easier to deal with. So if you differentiate both sides with respect to x, you will get a negative 2x dy by dx whole square plus 1 minus x square into 2 times dy by dx into d2y by dx square. This is what I had explained in the previous question as well. And the right hand side is 4 dy by dx. That definitely turns out to be nothing but on dividing by negative 2 dy by dx, rewriting simplifies to be the expression that we need to establish. So the key again is in cross multiplying before you take the second derivative, and squaring goes by the, again, the function that you have, by the required answer that you have. So this is something that with practice you will gain the confidence of doing and not doing. And then also the given y makes the difference. So y is square of sine inverse x, and that really helps to plug it in and makes the next step so much more easier. So hopefully you have managed to keep along with what I have done today. And now I'm going to stop this slide and get back to a few doubts that I can see coming up on the right side and see if I can help you out with it. Right. So all right. Is this the question that Tanmay had asked? So we cannot find the second derivative of x and y and then divide. Perfect. I'm glad, Tanmay, you have brought up this doubt, if this is what you were asking or saving for the end. So what? Let me elaborate on what Tanmay has asked. Tanmay says, can we not find the derivative, second derivative of x and y and then divide? This is in reference to the parametric differentiation question, right? So I'm going to open up the slide and tell you what exactly is wrong with what he's saying and why we cannot do what he's suggesting. So let me again just get back to the presentation and take a look at the question on parametric functions. So what we are looking at is that dx by d theta and dy by d theta has been calculated. Dy by dx is negative tan theta. We've sorted that out. Now, when you talk about d2y by dx square, you must know that this is the derivative of dy by dx with respect to x. It's not the square of the dy by d theta divided by square of dx by d theta. It's also not d2y by d theta square divided by d2, because we are not finding the derivatives of the dy by d theta with respect to theta again. So you cannot find the derivative of the numerator, that is dx by d theta, with respect to theta again, and d2y by d theta square, and then take the quotient. You have to find the derivative of dy by dx with respect to x, not dy by dx with respect to theta. And otherwise as well, it will be meaningless to just take the quotient of the second order derivative of x and the second order derivative of y and take the quotient. So you need to be careful with how and what you simplify there. Right? Is that clear now? All right. So that helps you possibly clear up your doubt. And if you still have doubts, you're most welcome to post it on Edmodo. And I will be in touch for our next session. In the meanwhile, go ahead, practice some more questions from NCERT and Smart Skills. All right. Take care. Have fun. And I'll see you again. Bye, everyone.